I want to try to explain how you might use LTSpice to do a Six Sigma analysis of a design. LTSpice is a free circuit simulation program from Linear Technology, um, and I'm going to use that and Excel spreadsheets to come up with a final answer. And the circuit I'm going to simulate might be that of a voltage regulator with a 3.3 volt output and an accuracy of plus and minus 5%, as I got noted right there. The transfer function can be modeled with an op-amp circuit where the output voltage equals the reference voltage times 1 plus the feedback resistor value divided by the value of the resistor that goes to ground. When you run that simulation, you could then go through and derive these values that are part of a Six Sigma analysis. And ultimately, you're looking for this CP index or CPK, and typically you want that to result in a value that's greater than or equal to 1.33. LTSpice has a Monte Carlo function and a Gauss function, and it turns out that say a 1% resistor, which this is right here, an tau of 0.01, and then all of its error terms: temperature coefficient, life stability, soldering, temperature, shock, humidity, terminal strength. If you go through the data sheet on a resistor, you'll find all of these error terms um, and what values to use for each. And when you take the square of the sum of all of those terms and then take the square root, assuming a normal distribution, you end up with a 3 sigma of the standard deviation. So when you do this RSS calculation, that's what you will end up with. And this Monte Carlo function and the Gauss function are related in a normal distribution. If I take the RSS value, TOL, and divide it by 3 and plug it in the Gauss function, and I take the tolerance value and plug it into the Monte Carlo function, if this is all working the way it's supposed to, and it did, you find that the Monte Carlo function is 3 times the standard deviation. So that's why that is there, just to prove to myself that LTSpice did a good job of generating the numbers for these functions, and that I did in fact understand this relationship correctly. And what I didn't find in LTSpice was a way to calculate the standard deviation of the population generated when you run this simulation. So what I did was I ran it once with just none of these things being calculated, and took the result of V out and V1, let's select both of them, and exported that to a file, and I already did that. So when I did that and opened that and saved it as an Excel file, I ended up with a standard deviation for the 1% resistors and a standard deviation for the 0.1% resistors. went back to my simulation file, plugged that in, and re-enabled all of these things to be calculated, ran the simulation a second time, and when I did that, in the error log, you get your result of all those measure statements where the 0.1% CPK value was 3.5 and the 1% CPK value is 1.15, which is below the 1.33 requirement. So if that's a hard, fast requirement for you, that kind of forces you to use 0.1% resistors. If you're really sensitive, you might, say, well, I only need one 0.1% resistor to push this just over the limit because we're pretty close. Anyway, you can play those games where you find the components that your design might be most sensitive to. And so that's basically how you do that. Now you can use Excel to do a lot more powerful stuff that I'm not going to go through, but you can generate random numbers, and you can do a normal distribution and generate your population. If you know the transfer function, you don't need to use LTSpice, but if it's a complicated circuit and maybe you don't readily know how to do that transfer function, you can run this simulation and still get a good Six Sigma analysis out of it. The other thing that's kind of nice to do is show things graphically, and you can do that with the histogram function. I'm not going to show you how to do that, but this is a nice tool to show things graphically. And that is about it. Am I forgetting anything? Let's see. Well, you can learn all of these things from the help file. So LTSpice has a nice help file where it'll show you how to run these Monte Carlo analysis functions. Basically, you need to step your analysis however many times you're going to do it, in this case 5,000 times, just so it runs this thing with a new random set of numbers 5,000 times. That's all this statement does. If you go through the help files, it'll explain all of these other things. The spice directive.op is just telling it it's running the DC analysis on all of this design, and it's going to run a DC analysis on all of those design pieces of this design 5,000 times and put the result in the SPICE error log if you have any measure statements. Otherwise, it'll graphically show you whatever node or current or whatever you've clicked on. I hope I wasn't too confusing, and I've gone over enough information that what I've done makes sense, and you can use these tools on your own to kind of get these ideas a little more gelled in your mind, rather than trying to do it all right here in what should have been a short video. Hopefully it is short enough. Okay, later. That's all.